Some time ago, I saw Ben Eater's video of running Apple One software, the monitor program, on a 6502 breadboard computer. And that got me to thinking, seeing the Nintendo Famicom or NES has a 6502 processor in it, could this software be made to run on a Famicom? The answer is yes, but I did need to add a lot more code. Because in an Apple One or on the breadboard computer, you have some chips that are specialized for reading in input, especially for reading keyboard input on the Apple One, or the serial chip in Ben Eater's breadboard computer, and writing out to the display. In the Apple One, you have a chip that's specifically designed to take in ASCII characters or command characters and to just put them onto the screen one after another. So that chip will manage the display of text for you. The Famicom does not have something like that. You have to write that yourself. So I had to write all the handling for input and the output into my code as well. So in the end, I get a much longer program than just wozmon, but we get there anyway. So firstly, let's have a look at the code, and I'll bring it up on screen and we'll see how it works, shall we? So we have to start. I'm including this keyboard S. We'll look at this keyboard file later. It has all the keyboard handling. We have to start off with a header for emulators, basically. If you run this in an emulator, this will configure the emulator. The segments in there, that's normal. We start off, most of these variables are the same as was monitor, right? And I think they're in the same locations. But I've added this here, a reset detection. I have a primitive form of reset detection, because usually when you start up a Famicom program, NES program, you want to clear off RAM, and when you reset, it's the usual process you do. And so what I want to have is a little reset detection. So if you're writing a program into the memory and then you reset the console, you don't wipe that program you've written, but at least you can sort of reset back to a known state and get back into the monitor properly. And so I've got a reset detection here. Uses 4 bytes. You got your normal values, and then we've got all my new variables for scrolling. I know I'm going to trigger some people with a mix of capital and lowercase variable names. Don't worry about it. And then some more variables. A bunch of registers for PPU control and reading the joypads. Where my input and display buffers sit, and the pointers for the interrupt jumps. Right, and so we've got a lot of it's just starting off with a lot of the normal NES Famicom preparation code, right? Setting up the Famicom, setting up the scrolling. The scrolling will always reset. So if you're scrolled to the bottom of the screen and you hit a reset, it will actually push you back to the top, right? You don't want that to keep you at the bottom if you reset. My reset detection is very simple. All it does is check 4 consecutive bytes for a hex 00, 01, 02, 03. When you power off the console and turn it back on, the memory is in a garbled, unknown state. So the likelihood that you get 4 consecutive, like 00, 01, 02, 03 is, I mean, it's essentially 1 in 4 billion, but there may be other factors that will affect whether you get sort of consecutive values turning up in RAM. So that's essentially how I check for if it's a reset or if it's a power on. But if it is a reset, then I only clear out the input and output buffers, display buffers, and I reset them. And I also reset the interrupts in case the user has changed where the interrupts jump to, like the NMI. You change where the NMI jumps to and you reset without, resetting the NMI interrupt location, it will it'll display nothing on the screen. You'll be stuck. So if there's a power on, you're clearing out memory as normal. Set up the reset detect known values 0, 1, 2, 3, 0, 1, 2, 3. Set up the NMIs to the normal values, default values, I guess you call it. And then you got more of your standard Famicom things, right? You're loading the palettes, clearing the name table, memory, and attributes, RAMs. You're loading the char. In my case, I'm using char RAM for my custom cartridge. Has no onboard char RAM or ROM. Then we enable the rendering. Yep. And then we've got this initialized keyboard. We'll go over the keyboard code a little bit later, but essentially it's going to check to see if either the keyboard mouse host compatible keyboard is present or if a family basic keyboard is present. It should work with the official family basic keyboard. I haven't tested it, but it should work with the official family basic keyboard. I mean, I've tested it in an emulator, but I haven't tested it with the real one. Right. So once one of those is detected, we will move into monitor, right? And so we start wozmon, call it wozmon, whatever. And we start our scroll, we set up our scroll, right? And then the rest of this, most of this is just standard wozmon, right? Including these values for ASCII values. For whatever reason, the keyboard input on the Apple I has the most significant bit set. Bit 7 is always set, so you get hex 80 and above. For most keyboard inputs, those values are the release characters. So when you press a key down, it would say space, which is hex 20, it sends hex 20 to your computer, and when you release it, it sends hex A0 to the computer. So you've got with the most significant bit set, it's the release keys. I don't know if the Apple I has that reversed, or if they specifically wrote this around reacting to release keys, but I'm using the release codes. That's fine. I could leave that the same. Our big change in my one starts here, using the VB wait to wait for keyboard reads, and once there's a key to read, we try to load it, and if we got a key from the keyboard, then we'll fall through this branch. Otherwise, it branches back up over here. So, I mean, it's essentially the same process from the original code, but we're jumping to different places. And so most of this is all the same as the original wozmon until we get down to the echo, where we've got quite a bit different because I have to manage actually printing to this screen with the Famicom rather than, throwing the ASCII code to the display chip and it will handle it. So I have to back up A. A will be the ASCII code, store Y in, which is my sort of offset for the input buffer, load the Y out, which is the offset for the output buffer. We're checking if it's a new line. If it's a new line, then we branch down to this one here, clear line. Otherwise, we convert the ASCII code to the code for the character that's in the name table. And then we store that into the display buffer. We increment that display buffer offset. We wait for the V blank, so it'll actually display on the screen. Then we check, this has got to check here to see if our offset is above like 31. And if it is, then it will do a clear line or go to the next line. So if you write a program in memory and you run it, this will be checking to see if the output of that program gets to the end of a line, and then it'll move down to a new line automatically. It's only necessary when you're running programs, essentially. Otherwise it should take care of this itself, but that's right. It's fine. Things are fine. Right. So if it clears a line, then it will reset that Y to 0. Then it loads A with 20. And it stores that in the display buffer. This 20 value is the @ symbol. And I'm using that to be like a cursor on the screen. It's not flashing, but it's just on the screen to show where you are typing. Stores it in display buffer, stores the Y, that Y offset into memory there, and then loads that input offset again and restores that A, because it might be needed again. And then we've got all this extra stuff, the VB wait, NMI handler. This one here I've got 3 effective addresses that you can use for each of the NMI and the IRQ, for if you want to write your own handlers in memory. We've got our NMI. We're still using sprites. The sprites can be done, but most of the standard NMI stuff going on. We read our keyboard in the NMI looking for any new characters, and we've got this big clear line and doing our scrolling, and that's all the code in the main code there. And then now we've got all the keyboard code, which is a lot. I'm not going to go over all of it, but we'll just do a quick go. So we've got an init thing here, which will first it's going to check for the family basic keyboard. If we find it, we store it in the init. If it doesn't find that one, we'll check for the keyboard mouse host keyboard. And if we haven't found it, then we'll VB wait and then jump back to the init. So it'll just sit in here until we find a keyboard that works. Keyboard ready, this gets called during NMI, and it'll check the buffer, the keyboard buffer, and it reads keyboard if the buffer's empty. Read keyboard. This gets called in the main program to read the keyboard buffer. I've got here use compare flag to decide what to do. Before it returns, it will compare with 0, 0, and so in your program you can use a branch immediately after, which is what they do in wozmon, to decide what you're going to do when it comes back from read keyboard. So if it's equal to 0, it's invalid, it's not a key. If it's a minus, if it's a negative value, then the key is released. If it's a positive value, then a key has been pressed. We've got this check mod keys set to alter the keyboard key codes. So this is mostly for like shift keys. I've got a shift map. So it will convert some, I haven't done all of them, but some key codes like colon, semicolon, quotes, quotation marks, exclamation marks, those sorts of things. Convert them to their codes if the shift keys are down. Read the input from the keyboard mouse host. Send the mod keys 1 byte, which sets all the values of the mod keys, or holds all the values of the mod keys, Shift, Control, Alt, and Windows key on both sides of the keyboard, left and right. We've got for reading the family basic keyboard, so it'll read whichever one it needs to, whichever one is detected, and the family keyboard mod keys, send those up as well. Delay for family basic keyboard. Here's our convert ASCII. It converts the ASCIIs to the character map values, the character map tiles, and then here we've got our family keyboard map and the shift keys and the keyboard mouse host ones and their shift keys, and then our palettes, and finally the tile data is included at the end. So that's got like 430 lines, a little bit too long. So let's get this running as well, shall we? Let's have a look. Alright, there we are. And it's not, oh yeah, no, it's looking okay. It's alright. See, you got the backslash and the @ symbol, which shows that it's there and it's working. Our address, our wozmon, is found at address 8000. So you can see 8000 is A9. So you can do a list of values. You can do memory. We'll do from 0, shall we? Right, you can look, this is memory, it's cleared, memory has been cleared. You can write values to memory. I'm using Ben Eater's one. Right. And this is where I should be able to demonstrate the reset detection. So, you can see that the memory has stayed, even though I've reset the console. So you can put values in memory, you can show memory, you can print. I'm not going to print the program because it's quite long. It'll take too long to print it all out. But You can do some of the example programs. They have to be changed a little bit. So I'm going to do the one that prints out all the characters. For E, for E8, 8A. I think that's alright. Then for, what was it, 4C20. Right, so if I print this, right, you can see the program is there in memory, and if I run it, is it working? Oh no, did I make a mistake? I probably made a mistake somewhere. Let's see, where am I? 844E, that should be right. E88A, that should be right. 4C20 should be right. I just ran this. I may have made a mistake by running it after. I think what I did wrong. Wait a second. 0 is A9, isn't it? Yep. We're looking all right. I think we're all right. Oh, there we go. So there's a little bit weird, right? There's a lot of characters that I don't have in my character set. So you get a lot of blank lines, empty space. This is not the compact one. You don't have the lowercase characters in this character set. But as you can see, it's printing out all the characters that it can on the screen. And it's just keep going forever. So that's one of the examples we can do. Alright, reset that. You can see it's still in memory. But there are some other things that you can do with this on the Famicom. You can do some longer programs. They can do some more interesting things, maybe. See, one thing that we've done or kept available is sprites, sprite rendering. So, we've got this longer program here. And essentially what I'm going to do, if I'm correct, I've got a 2 there. And then I've got 10. E8, 20, 4, C. Now if I've done that correctly, what I've done is I've put a character into the memory. Have a quick see. Did I have to write something into there first? I can't remember. No, I didn't. So that is a sprite. Which is part of the reason it's white. It's just a sprite that's running across the screen now. And because it's stuck in this loop, it's not taking any input from the keyboard anymore. We're stuck just in the that program. And so what I can do though is I can reset it there. I'll just do that there. And the sprite is still on screen because the sprite is sitting in memory. Right, we have the sprite's X and Y coordinates, 45, 45. Sprite number 4 with the attribute of 4, and it's just there, just sitting on screen. Yeah, so this is wozmon running on the Famicom, and you can do all the wozmon things on it, and you can use a normal keyboard so long as you have like my interface or a Family Basic keyboard. But this is not the end of Apple I software or just software in general running on the Famicom. I've got some other things to demonstrate. Of course, all my code is available in the GitHub link, which I have below. and I hope some people can enjoy. We'll see you again.